I'm Dr. Zhu. So today, together with my collaborator Chen Ceshi and Zubai Zhang, we will give a masterclass on our recently released machine learning platform for developing drug discovery. So the platform is called TorchDrug. And also thanks Connected Data World for giving us this opportunity to give a masterclass for all of you to enjoy this wonderful platform. So here is a brief outline of today's talk. So I will first give a brief introduction of the whole platform, and then I will teach you how to manipulate the data structures as well as use the graph operations built in our library. And then later, Zuobai and Chen Ce, they will give you more concrete implementation about the different drug discovery tasks like pre-training and fine-tuning as well as molecular generation. So let's get started from the introduction. Why we are motivated to develop such kind of platform for drug discovery. So as you may know that machine learning, especially graph machine learning for drug discovery is a really emerging field in recent years, especially in last year and this year due to the pandemic of COVID-19. However, for us, like researchers in graph machine learning community, it seems to us that we need much domain knowledge to implement the models in this field. And what makes this even worse is that if you compare different projects that's already implemented in this field, that almost every project is implemented from scratch. And that means that it's hard to compare across different data code base, hard to reproduce the results. And when you try to develop some kind of big pipelines, so it's hard to integrate the projects or scale up the existing implementations. So we wonder if we can somehow alleviate this kind of issue by building a new infrastructure to accelerate the research and development in this field, and that's TorchDrug. So to give you an intuition, what things look like before the presence of TorchDrug. So when you try to implement a popular model, say pre-training graph neural networks on molecules, so you first need to learn the RD-kit to train, and then learn some chemical knowledge. And then you need to implement conversion functions between different formats like RD-kit, NetworkX, and PyTorch. Simply because that you need to use RD-kit to process your chemical properties, and you need to use NetworkX to process your graph features like shortest path distance, like connected components. And finally, you convert everything to PyTorch to feed it into your PyTorch models. So every conversion function may look like something like this. This is a conversion function from RD-kit to PyTorch. And you need to write 3 by 2, which is 6 conversion functions altogether. And plus some other processing code, it typically takes around 1,000 lines just to process the data set before you building any machine learning models. And it's hard to debug. And it also can't be accelerated by GPU because NetworkX and RD-kit, they are purely CPU libraries. And in some cases, your machine learning model will be bounded by the implementation of RD-kit and NetworkX. And that's not what we want for efficient training and inference pipeline. So to see the challenge of implementing this kind of molecular stuff, so one challenge is that a molecule is a kind of non-grid structure because they are graphs, and they have different number of nodes, different number of edges. This is quite different from other domains like image, like natural language processing, where for image you can always crop it into the same shape, and for natural language you can always use padding and cropping to get it to the same length. But for graphs, like the 3 graphs here, we see that, okay, they have different number of nodes, different number of edges. So how can we efficiently process them together as a single tensor on GPU? And that's a very challenging thing when you implement it. And the last motivation comes from the development of software. We noticed that in software development, we don't want to write everything from scratch, and we want to use existing implementation as much as possible. And also, from the perspective of research, we need some kind of consistent interface for similar components. so that we can easily conduct ablation study or maybe do some contravariate experiments. So this covers things like data containers, data sets, layers, models, as well as distributed training and inference. You don't want to reinvent the wheels, and neither do us. So this motivates us to develop the TorchDrug platform for this purpose. And our platform draw much inspirations from popular frameworks like PyTorch and PyTorch geometrics. We borrow the imperative design of PyTorch, and we borrow the efficient mini-batch implementation of graphs from PyTorch geometric. But we extended more to graph machine learning on drug discovery. And here is an overview of the whole structure of TorchDrug. So the library is divided into several hierarchical levels. On the low level, we have the data structures and the operations, covering structures like graphs, and a specific instance of graph is molecule. And we also have the data set. And on top of that, we have everything just like other deep learning libraries, from layers, models to standard tasks. So currently we have 5 tasks from property prediction, pre-training, molecular generation, retrosynthesis, and knowledge graph reasoning. And more tasks will become in the future, including some tasks maybe on protein representation learning. And on top of that, we have the engine that manipulates the training evaluation across either single CPU, single GPU, or even distributed training settings. So this is all about the introduction, and for the rest part of the masterclass, we will give you a hands-on tutorial from the data structures, and then move on to the tasks like pre-training and molecular generation. So let's take a look at the data structure exercises. So I think my collaborators has already sent the link in the chat, so that you can also open it locally in your browser, and then you can run it. But you can also just view the shared screen and see our demonstration. So here comes the data structures and the graph operations of TorchDrug. These are the very basic and also fundamental building blocks in TorchDrug. So first, let's install the let's install TorchDrug on Colab. So this typically takes around 30 seconds if you already have PyTorch installed. So just to use pip install TorchScatter and then pip install TorchDrug. Yeah, I think it's almost done. Yeah, okay, it's done. And at the very fundamental part of TorchDrug is the graph data structure. So graph are just the first-class citizen in TorchDrug. And we first import the data module of the TorchDrug, and then we can define a graph using different formats. So here we just demonstrate with the format of age list, where in age list, every age is represented as this is the source node of the age, and this is the target node of the age. So it may take a while if you import TorchDrug for the first time. It takes a while. Okay, and here comes the result. As you can see that we can visualize the graph like this. So there's a link from the 0th node to the first node, just as defined in the age list. And we can also print the graph.adjacency. So here for better visualization, we just print the dense version of the adjacency matrix. While you can also print the sparse version of the adjacency matrix, which is the default graph.adjacency here. So that the sparse version is less readable, looks like this, but it's actually equivalent to the dense version. And you can pass this kind of adjacency matrix to your any favorite message passing graph neural networks. And by default, the graph is defined as a directed structure, and you can also convert it into an undirected structure. You just call graph.undirected. So this is quite analogous to the kind of operations over PyTorch tensors. You just imagine that the whole graph is a PyTorch tensor, and you can call it some function to manipulate it. And then you get an undirected graph with the adjacency matrix be a symmetric matrix here. So in some cases, we may also want to represent graphs with age relation types. So this can be easily implemented by extending the age list with another attribute. So this attribute indicates what's the age type for each link. So here it means that the link from source node 0 to node 1 has a relation type 0, and then we have a relation type 1 here. And we can build the graph correspondingly, and then we got this graph. And a specific instance of graphs is molecules, which is very, very commonly used in all kinds of drug discovery tasks. So TorchDrug provides native support of a molecular data structure. So we can build a molecule from a SMILE string. So a SMILE string just is a notation defined by computational chemists, and they use this to describe any kind of organic compound structure. So we build it into a molecule, and we can specify the node features we want for machine learning models. We specify the node features to be the position of each atom in the compound, and we specify the age feature to be the length of each compound. Well, in some cases, other cases, you may use more advanced features and just check out our list of features provided in our library. And we can visualize the molecule we define here. And we can also print the more .node features so that we can obtain a node feature. We can also take a look at the node feature here. So here the node feature is the 3D coordinates of every atom. So by default, because there is no confirmation information embedded in the compound, so when you generate the 3D structure of the compound, is actually projected onto a 2D plane with the z-axis to be 0 across all the atoms. So this kind of stuff can be used as just the input features to your, say, graph neural networks. And the molecule is also a container that consists of a lot of important chemical properties. For example, one important property is the formal charge of each atom. That is, whether an atom is positively charged or negatively charged here. So we can visualize it like, say, okay, we have the atom C. So this might be some carbon atom on the benzene ring, and it is electronic neutralized. And for the nitrogen atoms, they are positive charge. And for the oxygen atoms, some oxygen atoms are neutralized, and some oxygen atoms are negatively charged, as you can see in the figure. And another kind of graph is knowledge graphs. So this can be used to represent biomedical knowledge extracted from, say, PubMed papers text data. And you can use this kind of fact to do some reasoning task over the knowledge graphs to do things like drug repurposing, or maybe try to identify the target for a new disease. So here we show how to manipulate knowledge graph structures in TorchDrug. So we demonstrate this with a standard dataset called HashingNet. So first we import the datasets from TorchDrug, and then we download the dataset. So it will be automatically downloaded from the official website, and then it will load it and return the dataset structure. So here we have the HashingNet loaded, and it contains more than 45,000 entities, 24 relations, and more than 2 million triplets. So we can have an idea what the knowledge graph contains by taking some edges of the knowledge graph. So here we just take the very first edge of the knowledge graph, just extract the edge list 0 and get HTR here. And we send the head entity into the entity vocab to get a human readable string of that. And we also get a human readable string of the relation as well as the tail entity. And as the output shows that this edge contains the gene regulation relation between gene 11344 and gene 7485. So this means that this gene interacts with this gene. And our data structure is not only serve as a container for a lot of dominology stuff, but you can also manipulate the data structure with some built-in graph operations. So this is quite analogous to the manipulation of PyTorch tensors. You can do, say, tensor sum, say you try to sort the elements in a tensor. And we can also do the same thing in TorchDrug, just applying it on graphs or on molecules. So before that, we first introduce how can we create a batch of molecules in TorchDrug, because every operation in TorchDrug can benefit from GPU acceleration, and it's better to process them as a huge batch so that you can benefit more from the GPU parallelism. So here we create a batch of molecules from a SMILES list, and this SMILES list contains 4 molecules, and then we create the packed molecule, and we visualize it. As you can see that here we have a batch of 4 molecules. And we can send it to GPU device, and then we can process the molecules on GPU. So it takes a while if you pass the molecules to the GPU for the first time. And now we have the packed molecule, and it's on device CUDA 0. Just like original PyTorch tensors, we can do indexing like molecules.repeat. So this is very, very similar to the tensor.repeat. You just repeat the tensors. But for molecules, now we have double number of molecules in this batch, and the first molecule is the same as the 0th molecule. This is exactly the same as tensor.repeat. And we can also do indexing, like we just pick the 0th and the second molecule, just to pick these 2 molecules from the batch. And besides doing graph level operations, we can also do some masking over the node or maybe over the edges in the graph. And this can create different kinds of molecules. So here we show an example of masking out bonds that contain no carbon atoms. So we create such kind of edge mask by first extract the edge list to get the source node, the target node, and the bound type. And then we create an edge mask based on if the source node is a carbon or if the target node is a carbon. So if both nodes of the bond is not carbon atom, then we just drop the bond. As you can see that this kind of mask drops the bond between the sulfur and the phosphorus so that we break the first molecule into several fragments. And we also break the second molecule, this molecule into 2 fragments because there is a bond between 2 nitrogen atoms. So we can further extract a single connected component as a separate molecule, and this simply by calling Morse.connected components. So this is quite similar to the connected component functions in Network X, but it is purely implemented on GPU so that you can benefit from the GPU acceleration. And it also provides end-to-end differentiation so that if you build some models that depends on the graph data structure, then it can be end-to-end propagate the gradients. So we obtained the following connected components. So the first molecule is divided into 5 components, and the second one is divided into 2 components. And there's also a return value called number connected components, and it shows that the first one is split into 5 components, and the second one is split into 2 components. So we may further store the SMILES of molecules so that you can create the fragments from these SMILES for next time. So this kind of operations is quite commonly used in fragment-based drug discovery when you try to generate molecules by combining different fragments into a huge molecule. Another kind of operation commonly used in TorchDrug is to retrieve some specific edges from a graph. So this kind of usage is a typical usage for this kind of operation is on knowledge graphs when you try to answer queries like what are the symptoms that the asthma presents. So to answer this question, so we can create a kind of search pattern asthma presents and in something, and then we search what is the something here that asthma presents in. So we obtain the entity of asthma just by taking the its disease ID and obtain the corresponding entity in HashiNet. And we also obtain the relation for presents. And in order to denote the any, which is the question mark here, so this is a kind of wild card in the match, and we use -1 to denote any wild card or denote matching of anything. And then we create a pattern based on these three elements. We create asthma, any, presents. So note in TorchDrug, every relation happens at the third element of a triplet. So asthma, any, presents, and then we create the pattern. And because our kg.match supports a batch of patterns, so that you can simultaneously match a lot of patterns. So here although here we only have one single pattern, we can show that we create the pattern into a patch, because you see that the pattern has a shape of 1 by 3, where this 1 is the batch size and 3 is just this 3. And then we use kg.match the patterns to extract the corresponding edges that can be retrieved by the patterns. And we retrieve the edge index as well as the number match for each pattern. And then we send the edge index into the edge list to get the corresponding symptoms that present in the edge. So this can be visited simply by kg edge list edge index and access the first element of the edge list, which is the symptoms corresponding to this any here. And then finally, we translate the symptoms using the entity vocab provided by the HashiNet. So we have this kind of symptoms. So all these symptoms are directly related to the asthma disease. And although we provide a lot of domain knowledge directly encapsulates by our data structure, in some cases, you may also want to register your own attributes, especially you compute something based on some basic attributes and then compute some fancy attributes. So this can be achieved by the registration mechanism in our library. So we can register something like a node attribute. For example, here we define a node attribute called attached to C. So attached to C means that whether an atom has at least one carbon atom as its neighbor. So this can be computed by these 2 lines of code. And then we assign the attached to C as an attribute of the molecule, wrapped by a context manager with more.node. So this line, the context manager, means that we are trying to assigning something to this molecule as a node attribute. And then it will remember, okay, the molecule now have an additional node attribute called attached to C, and it will be automatically maintained during all kinds of graph operations, or maybe edge operations, node masking operations. So as you can see, we still use the example of TNT compound here. And the attached to C result is like the carbons are attached to other carbons, and the nitrogens are attached to one carbon, but the oxygens are not attached to any carbon atom. So if we apply some kind of graph operations like more.subgraph, and then we can take a look at the result. As you can see that the attached to C attributes is maintained just like before. So you can also define the attributes for edge level stuff or for graph attributes in the same way. And besides the data structures, TorchDrug also provides some variadic functions which could be very useful when you try to compute some, say, computer graph level stuff based on node level stuff, or compute edge level stuff based on node level stuff. So here we showed the usage of variadic functions based on a node selection problem. So the goal of node selection problem is try to pick a single node for each graph well, as you already noticed that different graphs have a different number of nodes. So this is actually a classification problem with variadic length across different examples. So different examples have a different number of nodes and different classification categories. So how can we implement it? Actually, in TorchDrug, we don't need any kind of padding or any kind of truncation operations. We just implement it as is, and everything can work efficiently. So to implement this, we just import the functional module of TorchDrug layers. And we first create some fake prediction, say just a random prediction of each node's logit. And then we can print the logit. So the logit contains the prediction for two molecules. The first molecule contains 12 nodes, and the second molecule contains 6 nodes. And we can split the prediction for different graphs, just use logit.split number nodes, and then we obtain the prediction for the zeroth graph and the prediction for the first graph. And in order to compute loss for this kind of classification with variadic categories, so we first define the labels. So here we just create some fake labels, just assume that the desired prediction is on the last node of every graph. And then we compute a variadic cross entropy between the logit and the label. And we also tell the function that we try to partition the logit with most.number nodes. That means the logit looks like this, and the logit is partitioned into the part for graph 0 and the part for graph 1. And then it will compute the variadic cross entropy across all the graphs without looping over each example. It just simultaneously computed very efficiently. And we obtain the loss for the graph. And as you can see here, okay, so the loss may depend on the random variable, and here the loss is 2.3. And during inference time, we can also use some variadic function to extract the top k nodes for each graph. So we first convert the logit into a probability using a variadic softmax, because we are still trying to dealing with something that covers a variadic number of categories. And then we extract the top k from each graph's node probabilities. We extract the top 3 probabilities for each graph. And as you can see the results here, so we have the first graph top 3 predictions to be the node number 3, node number 0, and node number 9, and their probability are 12%, 12%, and 10.5%. And this is for the second graph, and this is the node index in the second graph. So this is all for the tutorial part of data structures and graph operations. Next, I will give you some small exercise about this, and to see if we understand how to use TorchDrug to deal with some fancy stuff. So let's see the exercise here. Yeah. So in the exercise part, we just try to use what we just learned in the previous tutorial and try to implement some graph operations and also variadic functions. So here, the first exercise is about how to extract a k-core graph for a molecule. So a k-core graph is the maximal connected subgraph where all nodes have a degree at least k. So the k-core graph computationally can be obtained by iteratively removing nodes that have degrees smaller than k. So once, if you iteratively do these steps, and if you can't remove any more nodes, then you obtain the k-core graph. So here we implement the code to extract a 2-core graph for a batch of molecules. So here we have the molecules, and we want to extract the 2-core graph, which is already shown here. So this should be the result of 2-core graph. And your job is to implement the code here to fill the code and try to obtain the correct result like this. So it drops the side chains like the F here and the oxygen here, the nitrogen here. Just only keep the benzene rings. So I will go through all the questions, and after all the questions, I will give you some time to think about it and also to implement your own code to test it. So the second question is about how to do a more complicated search or retrieval on knowledge graphs with the match function. So here our job is to answer the query, what are the diseases that can be treated by both prednisone and oxyproline? So this try to search the common neighbors of prednisone and oxyproline indicated by the relation trait. So to search this, you may use a kind of fact that instead of computing two answer sets and intersecting them, we can compute the disease that can be treated by prednisone, and then verify if this kind of disease can be also treated by oxyproline, and then finally filter out the diseases that cannot be treated by oxyproline. So your job is to implement code here and to return the diseases variables, and then our model will print the diseases. So the correct answer has been shown here, but you need to implement the code for that. And for the last exercise, we will take a look at the variadic functions. So we will consider exercise that try to drop out exactly 50% of nodes for each graph in a batch. So this is a more rigorous version of the dropout applied to graphs than using native PyTorch dropout. So when you apply native PyTorch dropout to a batch of graphs, you randomly drop everything with 50%, but you are not guaranteed that every graph have exactly half of the stuff dropped. So here we want that every graph has exactly half of the nodes dropped in the dropout. But every graph have a different number of nodes, so you need to deal with the variadic length of nodes in this case. So the hint is that randomly selecting half of the nodes is equivalent to selecting the smaller half of a random permutation over nodes. So let's see how can you implement it using this kind of hint. So if you implement it correctly and then you obtain a mask called is dropped, and then our code will apply the dropout to the attribute, and also it will check if your dropout is correctly implemented. If it's correctly implemented, you should get something like this. You have 15 nodes of 13 nodes dropped, and you have 14 nodes of 28 nodes dropped in the second graph. So I think I can give you some time, maybe 5 to 10 minutes to try the exercise. And if you have any questions, feel free to ask me. So any volunteers for the exercise? Or anyone have any kind of thought for the exercise? Even if it's not perfect, you can just try to answer it. So here I can show you the answer to the first exercise. So this requires you write a while loop. You just write something like while moss dot degree in greater equal than 2 dot or, and then you write moss equal to moss dot subgraph moss degree in larger equal than 2, just as the command indicates. And you can try these things out. So we first try this one, then try this one. Oh, okay. It dropped the connection. Yeah, everything works fine, and the correct result we got. And for the second one, so I think we can try to write it. So we first create patterns that try to match the, say, prednisone. So prednisone treats something. So we add n equals to -1 here, and prednisone treats any disease, and then we got the match. And we can obtain the diseases by torch. So okay, here we forget a bracket, and we can get it by kg.age list, age index, and the first one. These are the compounds that prednisone can treat, and we can here we create a auxiliary variable once like disease. And we create another search that torch.stack. So this time we try to answer whether oxypronolines can treat this disease. So we just expand the treats with the ones, and oxypronolines expand with the ones, and with spin equals to -1. And we can do a match again. And this time, we only need to filter out the disease that doesn't match. So we just filter out disease that has a number match of 0, and we print the answer. So let's check if it's correct. Oops. Okay, they are missing one. So we need to load the dataset first, and then run it. Oh, okay, spelling mistake. Okay, it's done, and it obtained the correct disease that can be treated by both prednisone and oxypronolines. And for the variadic functions, so we first need to generate a variadic random permutation. So let's see, we just got some random permutation equals to functional dot variadic random permutation. And because we want to do a random permutation for every node in the batch, so we use moss.number nodes, and this creates a random permutation. And then we drop the nodes that has smaller value in the random permutation. So we just check is dropped equals to permutation smaller than moss.number nodes times 0.5. So we can check if it's correct. Okay, it's not correct. We need to broadcast this. And then we obtained that 28 nodes of 56 nodes dropped, and 31 nodes of 62 nodes dropped. So this is all about the exercise of this part. So any question? So if there is no question, maybe we can let Zuobai to introduce the second part on pre-training and fine-tuning.
Okay, so let me see how to share my screen. This one. Okay, so can you see my screen?
Yes.
Okay, thank you. So thanks for Zhao Cheng's introduction to the basic usage of our TorchDrug library. And now I'm going to show you how to build your own drug discovery pipeline with our library. Specifically in this tutorial, I will first demonstrate how to pre-train a graph neural network on molecules. And then I will show how to fine-tune these molecules on some downstream property prediction tasks. So as we all know, in many drug discovery tasks, it's costly in both time and money to collect label data. So typically, we will use self-supervised pre-training to leverage the massive unlabeled data. So in this tutorial, I will show you how to do the pre-training with our library. Okay, so the first step is still to install our library by pip. And then here I'm going to introduce two kinds of different self-supervised strategies to you. And these methods typically construct some unsupervised loss functions based on structural information in molecules. And note that for illustrative purpose, we only use the clean tox dataset here, which is much smaller than the standard pre-training datasets. And for real applications, we suggest to use larger datasets like Zinc2M. Okay, so the first method I want to introduce is called infograph. So infograph aims to maximize the mutual information between the graph level and node level representation. So here is a question: how can we approximate the mutual information between these two different level representations? Okay, so here is the solution. For example, given two different molecular graphs shown in the picture, we can first apply a graph neural network on them, and then we can get the node representations for all the 5 nodes in the two graphs. And after that, we can apply a readout function to get the representation for the two graphs. Sometimes the readout function will be a mean function or sum function. So to approximate the mutual information, we need to construct a contrastive loss. That is, we need to construct some positive node graph pairs and negative node graph pairs. So let's see. For example, in this picture, this blue node and this blue graph pair will form a positive pair because they are from the same graph. And this blue node representation and this red and black graph representation will form a negative pair because they are from different graphs. And our task is to predict whether a node graph pair come from a single graph or two different graphs. So this is essentially a binary classification task. And by minimizing the binary cross entropy, we can maximize the mutual information between the two level representations. So this is the high-level idea of infograph. And now I will show you how to implement this method in a few lines with our TorchDrug library. So the first step is to load our pre-training dataset, which is CleanTox here. So we just call the CleanTox class from the datasets module, and we pass the dataset into this class, and then we can set the node feature and edge feature as pre-train. So here, why should we set the node feature as pre-train? because we need to keep the node feature consistent between the pre-training stage and fine-tuning stage. So we can just set the node feature as some predefined pre-trained feature. Okay, after that, we are successfully defined our dataset. And then we can define our graph neural network. And here we will use gene. And we define a 5 layers gene. Then we can pass the node feature DIM and edge feature DIM into this model. And then we can turn on the batch knob option and set the readout function as mean. And after that, we can define our infograph model by passing our gene into this model. And in this way, we have our self-supervised model. And then to wrap this model, we need to build a unsupervised task, because we will use unlabeled data and we will construct some unsupervised loss. So the loss function will be defined in the model. And after that, we can define our optimizer, and we can pass the parameters in the task to this optimizer and set the learning rate as 1e minus 3. And after that, we can define our solver. And here we will wrap all the stuff into this solver. We just pass the task into solver, pass our data set into the solver, and pass our optimizer into the solver. And one thing to note here is that we only pass the data set as a training set and leave the validation set and test set as null, because here we are doing pre-training, so we do not have any validation and test sets. And then we can set the GPU as 0. In this case, we will train the model on number 0 GPU, and we can set the batch set as 256. In this way, we can define our solver, and after that, we can train our model for 10 epochs, and after finish training, we can save our model as a checkpoint. So as you can see, here is the log of the training procedure, and you can see the mutual information is increasing, which suggests our training is successful. And after we finish the training, we can save the checkpoint to this bus. Okay, so that's all for the infograph part. And next, the second strategy I want to introduce is called attribute masking. So the aim of attribute masking is to capture the domain knowledge by predicting atom times in molecular graphs from randomly masked node features. For example, in this picture, we are given a molecular graph, and we will randomly select a node and mask its features, so it will be marked as gray. And then we can apply a graph neural network on this graph and get the representations for the 4 nodes in the graph. And after that, we will use the representation for the green node to predict its atom times. So now, so here the atom time is just the oxygen. Okay, so that's the high-level idea of attribute masking. And I will show you how to build a pipeline of attribute masking. So essentially, it is very similar to the infograph. So we still need to define our data set first. And after that, we can still define our 5-layer gene model. And the only difference here is that we need to define an attribute masking task instead of an unsupervised task, because here we need to define our loss function in the attribute mask task. And also we set the mask rate at 0.15. And after that, we can similarly define our optimizer and solver for this task. And then we can train the model for 10 epochs and save the model as a checkpoint. So as you can see, the cross entropy is decreasing and the average accuracy is increasing, which suggests the model is trained correctly. And after all of this stuff, we can save the checkpoint into this path. Okay, so That's all for the pre-training stage. Now we will go into the fine-tuning stage. So when the graph neural network pre-training is finished, we can fine-tune the pre-trained model on some downstream property prediction task. And here, we will use base dataset for illustration, which contains over 1,500 molecules. And the label is just the binding affinity results. And first, we can download the base dataset and split it into training, validation, and test set according to scaffold. So we just split the dataset according to scaffold to make it more difficult, more challenging. And note that we need to set the node and edge feature in the dataset as pre-trained in order to keep it compatible with the pre-trained model. Okay, so after that, we will get our training set, validation set, and test set. Then we must define the same model at the pre-training stage. So here we just define a 5-layer gene model, and we can set up our optimizer. And one thing to note here is that we need to define our supervised task, and here is a property prediction. We need to pass the model into this task, and we will set the criteria and binary cross entropy, and set metric as AOPRC and AORC, because this task is a binary classification task. And then we can pass the task module, the training set, validation set, and test set into our engine. So here, because this is a supervised learning, so we need to pass the validation set and test set into our engine. So similarly, we can set the batch size as 256. And now we can load our pre-trained model from the checkpoint and fine-tune it on some downstream datasets. So one thing to note here is that we need to define a task-specific prediction head for each downstream task. So we only load the graph neural network to our downstream task. So the graph neural network, pre-trained graph neural network, will be stored in the model of checkpoint, and then we can load the corresponding part into our task. And after that, we can train our fine-tune our pre-trained model on the downstream task for 100 epochs, and then we can evaluate on some validation set. So as you can see, here is the training procedure. So the cross entropy is decreasing, and finally, we can get some performance on validation set. Okay, so that's all for this tutorial. And any questions here? So if no questions, maybe we can move to the next part. And okay, so I will terminate the GPU and connect this exercise. Okay, so I will leave some exercise for you. And in this exercise, we will implement the context prediction task, which is also a self-supervised learning task. And the implementation will be based on the operations provided in the graph data structure. And then we can test it on some downstream datasets. Okay. So I will first introduce the task to you. And the first step is still to install our library, myPipe. Okay. So what's the definition of context prediction? This task was proposed in the paper Strategies for Pre-training Graph Neural Networks, and it aims to use the subgraph representation to predict their surrounding graph structures, which we will refer as context graph here. So the question is, how can we define the subgraph and the context graph? Let's see. For a given center node, which is marked as red here, the subgraph is defined as a k-hop neighborhood surrounding the selected node. So let's see. For example, in this picture, k is set to 2, and the subgraph is just the 2-hop neighborhood around the red node. So it's just the 5 nodes in the purple square, including 1 red node and 4 blue nodes. So that's the subgraph. And the context graph is defined as the surrounding graph structure between R1 and the R2 hop from the center node. So for example, here we set R1 equal to 1 and R2 equal to 3. So the context graph will be the subgraph between 2 orange squares. So it contains 8 nodes, including 4 blue nodes and 4 green nodes. So that's the definition of context graph. And also we need to define the anchor nodes. Nodes between K and R1 hop are picked as anchor nodes. So here the 4 blue nodes are just the anchor nodes, and these anchor nodes will be used to extract the context representation. And so after defining the subgraph and context graph, we will first apply the context graph neural network to obtain the node embeddings in the context graph. And then we need to get a representation for the context graph. So we just take the average embedding of the context anchor nodes to obtain the context representation. And for the subgraph, we can get the representation by applying a graph neural network on it and take the representation of the center node. And the learning objective here is to predict whether a particular neighborhood, a particular subgraph, and a particular context graph belong to the same node. So it's just a binary classification task. We need to define some binary classification loss function. Okay, and so now I have already implemented the framework of this task, and I will need you to implement 5 sentences in this function. And first, we can just go through this function. And in this task, this class is just a subclass of n.module in PyTorch. So it will have an init function and a forward function. So in the init function, we will define our model. So first, I will explain the meaning of parameters here. So here we need to first pass the model into this class, which is the graph neural networks we want to pre-train. And we also need a context model to extract the representations for context graph. And by default, we will use the same architecture as model without parameter sharing. Oh, sorry. And then we need to set the K, R1, and R2 in order to define the subgraphs and the context graph. And also we need to define our readout functions for graph neural networks. And we need to define the number of active samples. So that's the definition for our context prediction module. And let's take a look at the forward function. So in the forward function, it is typically called in the training procedure. And here we will take in a batch at the input, and we will call the predict and target function to get the prediction and target. And then we can call the evaluate function to calculate some metric. For example, here, because this is just a binary classification task, we can calculate the accuracy of our prediction. And then we need to define some loss function. So here we need to define the binary cross interface between the prediction and our target. And then we can return the loss function and metric. So as you can see, the most important function here is the predict and target. And so in this function, we will take the batch as input, and also we will take the all loss and metric as input. So why should we pass the all loss as a parameter? Because sometimes we want to define some loss function in the model. For example, if you want to use L1 regularization, you can define the loss function as the L1 norm of all your model parameters. Also, that's similar for metric. And in this predict and target function, we can first extract our graph from the batch, and then we can call the substructure and context function to get the subgraph and context graph. And then we can take the anchor nodes by using node indexing. And after that, we can apply our graph neural network to get subgraph features and apply the context model to get the context features. And then we can define our positive and negative examples. And by calculating the similarity between subgraph representation and context graph representation, we can get our prediction. And we will return our prediction and target. And in the function of substructure and context, we need to extract the subgraph and context graph around some randomly select centers. So here we just first select some random centers, and then we will calculate the distance between all the other nodes to these centers so that we can extract the neighborhood. And after that, so the first exercise is to calculate the shortest path distance. And this exercise, in this exercise, I will need you to implement one iteration in the BFS process to calculate the shortest path. And one note here is that this exercise will be more difficult than the other four. And for the second exercise, after we get in the shortest path distance from the center node to all the other nodes, we need to define our substructure and context using the distance array. So we can just follow the definition of substructure and context graph. And then we can extract our center node and anchor node. And then we can set these as a node attribute to the subgraph and context graph. And finally, we should filter all the invalid context graph which contains no nodes. So here we need to define a Boolean mask by using this condition. And then we can perform graph index. And after that, we will return our substructure and the context graph. So that's all the details for our exercise. And maybe now I can leave you 5 to 10 minutes to finish this exercise. And if you have any questions, you can ask now. Okay, maybe I can share the answer now. Okay, so for the first exercise, we need to implement one iteration in the BIPAS process. And here, for each edge from X to Y, we can set the distance X as a message, and we can pass the message from X to Y. Then we can do a minimum aggregation on the node Y. And note that we need to add an additional one here because passing this message will take one step. So that's all for the first exercise. And for the exercise 2, we need to define our subgraph and context graph based on its definition. So because we have already got the distance array, we can just define the Boolean mask by comparing the distance with the k and comparing the distance with R1 and R2. So in this way, we can define the Boolean mask for subgraph and context graph. And for the third exercise, we need to remove all invalid context graph that contain no nodes. So here we can just check whether this graph, the number of nodes of this graph is positive. So in this way, we can define a Boolean mask over all the graphs. And after that, we can take the valid graph from the batch. So that's the answer for the third exercise. And for the next exercise, we need to take the anchor nodes from the returned context graph. And remember that we have already defined the Boolean mask for anchor nodes. So here we can just take the subgraph, use the subgraph method defining our graph structure. We can take the anchor node here. So in this way, we can take the anchor node from the context graph. And for the last exercise, we need to call our context model to calculate the features extracted from context graph, and then take the context feature by apply a without function. Okay, so here we can do this similarly as what we did for substructures. So we can just copy this line here and replace the model with context model, replace the subgraph as context graph. And similarly, we can take the node features for the anchor nodes. So that's the answer for exercise 5. And now we can run our model and then try to test our task on some downstream tasks. Maybe it takes some time. Oh, as you can see, the training is starting. Oops. Maybe it will take some time. Yeah, okay. So as we can see, the training is starting and the cross entropy is decreasing, which shows our implementation is correct. Okay, so that's all for this exercise. And next, I will stop sharing and leave the, maybe Chenze will introduce something about generation.
Okay. So now let me first share my screen. Okay.
We can't see your screen so far.
Yeah. Okay. I will just share my entire screen. Wait a second.
Yes. So now we can see that.
Okay. So now can you see the screen? Okay.
Yes.
Yeah. Thank you, Zhao Chen Zuobai, for the great talk. And next, let's move on to the third part, which is a tutorial about molecule generation. And as a convention, we just first install the TorchDrug with several lines of code. And I have already executed this cell. Yeah, and this task is called molecule generation. And this is a very fundamental problem in the field of drug discovery. And the goal of this task is to design generative model to generate novel molecules which has desired properties. And of course, the molecules should obey the rules of chemicals. And in this tutorial, we will implement two graph generative models called GCPN and GraphAF. And we will show to you guys how to pre-train these two models with the Zinc dataset. And also we will show how to fine-tune these models with reinforcement learning to optimize two specific properties called QED and penalized log P score. And these scores are two widely used scores in the computational biology. And also, I also provide an additional reading list, which contains a lot of papers related to molecule generation. And if you guys are interested in this topic, you can go to this list. Okay, so the very first step of building a machine learning model for drug discovery is definitely preparing the right data set. And also, this step is probably the most annoying step if a new beginner wants to dive into this field. And actually, our TorchDrug has provided a very nice module called datasets, and it contains a lot of common machine learning ready datasets for a lot of drug discovery tasks. And for this molecule generation task, we just use the predefined Zinc dataset called Zinc 250,000, and it contains 250,000 drug-like molecules. And you can just load the whole dataset with a single line called datasets. You can just call the function datasets.zinc 250,000, and you can pass the directory that you want to store the dataset, and also you can specify other arguments like whether you want to calculate the molecule and what's the node feature of the whole pipeline. And here we just use the simplest feature called symbol, and it is the atom type of each atom in the molecule. And this cell will take around 8 minutes. And in order to save the time, I have preloaded the dataset. Okay, so once the dataset is provided, we can start building our models. And the first model is GCPN, and it is a very popular model in this field. And the official code of this model is actually open source, but the code is very hard to use for new beginners, and it contains more than 1,000 lines. But in this tutorial, we will show you how to construct the whole GCPN model, pre-train and fine-tune it in a few lines of code. Okay, so now let's first construct the GCPN model. And the model consists of two parts, a graph representation model and a graph generative model. For graph representation model, we here use a relational graph convolution network. And you can see from the mathematical expression that it is basically a graph neural network that iteratively updates the node embeddings xi by aggregating all the node features from its neighborhoods denoted by xj. And here the R is the set of relations such as different edge types. And how can we build such a graph convolution network in our TorchDrug platform? Actually, it's very easier. We can just call the function models.rgcn, and you can pass the input dimension and the number of relation to this function. And also don't forget to specify the number of graph convolution layers in the function. And here we just use a 4-layer RGCN in this cell. And for the graph generative model, we use the tasks.gcpn generation to define the model. And here we just plug in the define the graph representation model called model, and then we should specify the all possible atom types involved in the generation, and we should also specify the maximum number of connections we should consider between the current node and the previous nodes. And we also specify the maximum number of nodes in the generated molecules, and also the training criteria. And here it is the negative log likelihood. Okay, so let's execute this cell. Yes, and then we have actually prepared all the stuffs we need to train the model, and we can define a solver by calling the core.engine, and we can wrap all the things together by passing the tasks, datasets, and also the optimizers into this solver. And also we specify the ID of the GPU we will use, the number of batch size, and also the log interval to the solver. And then we can call the solver.train to train the whole GCPN model. And once the model is trained, we can also save the pre-trained model to a directory specified by this path. And here I will just execute this cell for illustration purpose. And yeah, you can see the training is started, and it will take around 10 minutes to train a single app on this Colab. And here I will just cut the training procedure and to save the time. Okay, so you can see the training is started, and in each log interval, it will output the accuracy and loss, and also a lot of other informations you can refer to. Okay, and I will stop the training now. Okay, so once the training is finished, we can load the pre-trained model into the current model. Here we just download a pre-trained checkpoint from a Google Drive folder, and then call the solver.load to load the pre-trained model to our GCPN model. Yes, so the parameters is loaded. And now we can see what molecules can be generated from this pre-trained model. And here we can call task.generate to generate the novel molecules. And we can specify the number of samples we want to get and the maximum number of resample in each steps. And also you can specify the arguments for visualization, such as the number of molecules, a number of rows to show in a figure, and also the title of the molecule. Yes, here you can see we generate around 32 molecules, and they are shown in a single figure. So this is quite fancy, right? And so this is all about the pre-training. And in the real world de novo drug design, actually we want to generate molecules with desired properties. And so we usually need to fine-tune the pre-trained model using some algorithms like reinforcement learning, PPO, or other algorithms. And in this tutorial, we simply choose to use the proximal policy optimization to fine-tune the GCPN model. And here we just first construct a model and load the pre-trained parameters into this model. And here note that the whole cell is very similar to previous cells, but we here we set the tasks and the criteria, and we set the task to the desired properties we want to optimize. And here we use penalized log p, and the criteria is changed from negative log likelihood to PPO. Okay, so then we can just call the solver.chain to fine-tune the whole model using PPO. Yes, and the fine-tuning is started, and you can see the model comes with a very low penalized log p at the beginning, and as the training goes, you can see the maximum penalized log p score will increasing. Yes, and also in this tutorial, we have another model called GraphAF, which is a flow-based autoregressive model for graph generation developed by our group. And the whole procedure for defining the model, pre-training, and fine-tuning is quite similar to that of GCPN. And I will not repeat all these things here, but you can play these stuffs in your own collab with very simple codes. Okay, so you can see, let's move to the fine-tuning here, and you can see the maximum penalized log p is increasing, and after around 5 to 10 minutes, you will got some preliminary results, and it can match the reported performance in the original paper. Okay, so for this tutorial, I will just stop here, and I will move to another exercise. Okay, so let's first disconnect it from this collab. Okay, so this is terminated, and here I have a collab for exercise about graph generation, and let's connect it to this collab. And first, let's install the TorchDrug. So it's really simple. Okay, so this exercise is still about graph generation, and this is about the customized graph generation. And in this exercise, we will not do any training and also any learning. So we do not need the data set. And to save the time, we will just use a dummy data set. And the dummy data set will provide some very important information when you constructing your models, such as node dimension, atom type, or some other features. Yes, and we will first download the pre-trained GCPN model from the Google Drive, and we will also define a pre-trained GCPN model and load the pre-trained parameters. Okay, so now let me first introduce this exercise. And yes, now we have a pre-trained GCPN model, right? And we can see what we can get from the pre-trained model by calling task.generate, and we will generate 8 molecules. And by default, the model will generate molecules from a single carbon, which is the most common element in organic molecules. And so this represents the most common situation. Yes. The results is coming soon. Yes, we got 6 successful samples from the pre-trained model. And you can see all these molecules are indeed generated from the single carbon. And these molecules do not contain any rings and any benzenes. But in some real-world scenarios, the researchers or chemists may want to generate molecules based on a given substructure, or he wants to optimize existing substructures or generating molecules from specific functional groups, and he may not want to generate the molecules from a single carbon. And how can we customize such a generation function to achieve this goal? And this is what we will solve in this exercise. And here we define a customized generation function called myGenerate, and it will take a pre-trained model called task, and you can specify the number of samples you want to generate and the number of maximum resample you will use. And the most important argument of this function is the initial smiles. And this smile string specifies the initial substructures you will use, based on which the GCPN will sequentially add nodes and edges to these structures. So if you set the initial smiles to a benzene ring, such as this string, all the generated molecules will be based on these initial structures. So this is what we will complete. And I will first introduce the whole function. And you can see the function will first initialize very initial structures called graph. And you should initialize the graph from the given initial smile strings. And this is the first exercise you should complete. And once the single structure is initialized, you will call the repeat function by graph.repeat to repeat the single graph several times so that we can generate a lot of graphs for one function call for several samples. And then you should move the graph structure to a CUDA device. And then we will start the autoregressive generation procedure, and the following loop will be executed by several times. And in each execution, this function will determine the action that should be applied to the current graph, and it will return a new graph. And this is already handled. And what you need to do is to determine these new graphs. If this is the last step, you may want to collect all the graphs whose number of nodes are lower than maximum node. And you should append these valid graphs to the results. And if this is an intermediate step, you should determine the current new graph should be kept for next execution, or it should be collected to the results. And if the graph is stopped or it is reach the maximum number of nodes, then the graph should be appended to the results. If the graph does not meet these criteria, it may be masked as continuous, and these graphs will be fed into the next step for generation. Okay, so here are 3 exercises you need to fill. And once you finish this function, you can call the myGenerate function and specify the initial structures, initial smiles, to see what will happen to this generation model. And now I will leave you around 5 minutes to finish this function. And yes, so if you have any questions or have any ideas, you can tap in the chat box. Okay, so since nobody is interacting with me, maybe I can just show you the right answers. And actually, the first exercise is quite easy, and it is already covered in the basic usage tutorials by Zhao Chen. And as indicated by these comments, you should construct a graph structure using the initial smiles, and you can simply call the data dot molecule dot from smiles, and you can simply feed in the smiles. And don't forget to specify the other arguments you used during the data preparation, and you should keep this argument consistent. Yes, and here we just set the calculus to true and to set the node feature to symbol. And for the second exercise, as indicated by the comments, you should keep all the graphs whose number of nodes are no more than maximum number of nodes. And here you should use the feature of batch indexing of packed graph. And you can pick all the graphs that meet the criteria. And here the criteria is the number of nodes is less equal than maximum number of nodes. Okay, so for the third exercise, you should setting up a Boolean mask, and a graph is considered as continuous if the graph meets two criteria. The first criteria is that it should not be stopped. So the new graph should not be stopped. It should be non-stop. And the second criteria is that the number of nodes in the graph should not reach the maximum number of nodes. So we just simply copy the code and change the operation. Yes. So I think this is a correct answer, and let's see what we can get. Yes. So here we just finish all three exercise, and we generate 32 molecules using our customized myGenerate function. You can see that all generated molecules contains at least one benzene rings. And you can also play with these functions by using other initial smiles. For example, you can maybe use a very complicated smile strings. And let's see what we can get. Yes, you can see that all the structures contain, oh, oops. Some results may be invalid. Yeah, but anyway, you can try these results by yourself. Okay, so that's all about my part, and so maybe I think we have finished our masterclass, right? And I'm wondering whether anybody has some questions, and we can have a discussion period, and we still have around 20 minutes remaining.
Yeah. So any questions? Just you can either raise your hand or maybe send in the chat box.
Oh, I actually has found the box. Actually, here you should not use in this string. You should use the initial smiles. And let's retry this function. Yes, now all generated molecules contains these substructures. Okay, that's perfect.
So any question from anyone? Or if there's no question, maybe we can somehow end here.
Oh, I see the
I see a
is
question.
typing.
Yeah. Or you can raise your hand to just give a
Yes.
direct chat.
If you want, you can speak, and also you can type. So, what do you mean by future development goal? Development.
Yeah. Do you guys where do you what do you think this
Okay.
TorchDrug is maybe lacking right now, or things you want to improve with it, or where do you think in 6 months or a year or 2 years, torch functionality TorchDrug may have?
So an obvious way to improve TorchDrug development is to add support for more models and more tasks. So currently, as you can see, that we only have tasks for 5 popular tasks, but there are several other tasks beyond that. For example, tasks on proteins, or maybe more tasks on biomedical knowledge graph, like more specifically like target identification. So this kind of stuff. And we can also include more models. And from another perspective, that we may also add more library features, for example, to be compatible with other libraries, saying that being compatible with Python geometric, or maybe try to include more standard metrics, so this kind of stuff. And also the internal design could be somehow improved to further improve the efficiency of TorchDrug, although it's already very efficient currently. So yeah, we plan to maintain it for a long time, at least 1 or 2 years, or maybe somehow more than that.
Excellent.
Yeah. I think incorporating the spot for proteins is definitely one of the most important direction. Due to the pandemic, I think the protein modeling and protein engineering is actually very popular now. And this is what we plan to do next. Yes.
Other questions? By the way, I would like to mention that because TorchDrug is an open source project rather than a closed source, so we would like to rather gather community efforts from the users. And if you feel interested in contributing anything into TorchDrug, or you find the bugs, or you want to just propose new features for TorchDrug, just you can give a pull request or raise an issue just in GitHub. And we already received some of that, and some of the features are considered as future work for us.
So this the whole masterclass is recorded, right? And maybe it will be broadcast to other audience, maybe.
Yes.
I'm not sure.
Yes, it is recorded.
Okay. So I hope that more people can see this.
Yes, sure. So do you want to add something?
Yeah, we can share some. Maybe we can share some more links, Zhaozhen.
Yeah.
So, such as the homepage of the project.
Yes, and also there are some more tutorials on Collab so that you can play with that.
Okay.
So,
if it is possible,
sure,
maybe you can share this information with other audience.
And there are more Collab tutorials in this link. You can find tutorials for other tasks like retrosynthesis and knowledge graph reasoning just in this link.
Yes, and also we have a very, very nice post published in Medium, and it is, I think it is authorized by PyTorch.
Yes, and it talks about TorchDrug in a more interesting way, just like a blog post. Find the Medium link.
Yes, I have already sent
okay.
the link. Okay, so I think maybe we can end it now.
Yeah, maybe so
Yes.
much for today's
Today.
discussion and masterclass.
Okay, thank you all. I'm going
Yeah.
to. Do you want to add something? I can stop the recording on the session.
Yeah, I think you can stop the recording.
And the session. Okay.
Okay,
Thank you all.
okay.
Yes.
Bye.
Thank you.
Thank you for your
Bye.
efforts.
Bye.
Thank you. Bye.
Thank you. Too.
Bye.
Bye.